Okay, so what we've been doing so far is we have been using the time increment, so the number of seconds per frame, so to speak. But there's also the inverse of that. And let's take the inverse 1 over this, and that is the frames per second. Let's put it here, FPS. While this gives you the number of seconds per frame, this gives you the frames per second. Great. So in Mover, this is the value that you're setting. Normally, I think it's 2 milliseconds, 0.002 seconds, I guess. But we're going to play around with it. There's something else, the adoption rate, alpha, in this case 10%. So the inverse of that, let's take that, equals 1 over this. Now, what does that represent? And as you can probably tell, if I change the adoption rate to something like 5%, then this gives you a certain number. Well, the question is, what does that number represent? Let's take a look at a line. Now, let's take a look at that line that starts down here by the origin at the 1 second mark. And let's draw a tangent line that goes up here. And the important thing, this line is tangent right in this very point. Now, that line will intersect up here. And it will reach a point here that is exactly 20 frames off into the future. That's exactly those 20 frames. And it makes total sense. We're telling this line, the green line, the output graph, to make a 5% step for each frame. So after one frame, we make a 5% step. Well, that is equivalent to saying it would take 20 frames to reach your destination, to reach your target. So at this point, that tangent line means it is always pointing at a point up here where our current value would be 20 seconds into the future. That's where it's trying to get. The green line tries to intercept the target 20 frames off into the future. Now let's do this again. Let's take this and just for shits and giggles, put it here or put it anywhere on the output graph. That line again, the green line, a gradient that will take it to its target value, the blue one up here, in 20 frames. So at any point along this graph, let's do it one more time. We're here. And we want to reach our target somewhere, it's 20 frames off into the future. So this number gives you the amount, that number represents the frames off into the future it would take for you to reach your target if it was a steady value, a linear system. But as you can tell, that green line makes a curve. It doesn't progress linearly towards the target. That's what a simple moving average would do. It's not a simple moving average, it's an exponential moving average. So it keeps that property. And that's the reason why we use an exponential moving average and not a simple moving average and not a weighted moving average, because this is the property we want to keep. Step size in percent per frame, or the gradient pointing towards a point in the future that is this many frames off into the future. This line, I can draw this line for any point on the graph. It will always point somewhere 20 frames into the future. Now, why am I explaining this to you? The reason why I'm explaining this to you is this adoption rate is something that you don't set in the Mover software. It's something that probably is present in the background. I'm not even sure if it's in the code. It should be in the code actually as an alpha value, but what you in the user interface are setting is this one. So let's change the formula. This one, for example, is 20. And this one is a formula that says equal 1 over this value. Now what we're doing, we're entering this value and we're getting this value. And this is what in turn then generates the low pass filter. So I'm not sure if there is a catchy name for this. I'm calling this the target horizon. In another context, I heard the term receding horizon because basically it's the horizon that recedes. It's the point that the output of a low-pass filter is trying to get to. It doesn't have any further of an horizon than this. Well, think of it like this. Initially, the filter is blind towards what's going to happen in the future. So for the filter, the world kind of looks like this. And then an instant later, you're going to see up here, there's this one value showing up. All of a sudden, boom, there's a jump to 1. Now that's the case right now. So the filter takes up this gradient that you see on that red line, the red dotted line. So it wants to go to that new value within 20 frames. And in Mover, normally typical values are around 100 or 500 or 1,000. And given that the frame rate in Mover is by default 500 frames, 1,000 means that it's going to reach the target in 2 seconds if everything stays linear, which it doesn't. So now you can see as time moves on, that gradient is no longer the steep gradient that it initially was. It kind of shallows out. But again, here at this point, 2 seconds, again, the gradient that the curve takes in this very moment is such a gradient so that it would reach its target, which is up here, within 20 frames. And that's for every point in time, that gradient stays the same. That's one of the reasons why I call this the target horizon. I'm not sure if that's the technically correct term, but I had to give it some name in the code, and that's how I represented it. It's the amount of frames the output graph is projecting into the future. Now you could probably tell if you increase that number, the filter is going to get slower and smoother and smoother because it tries to reach its destination, it tries to reach its target over a higher amount of frames. So I'm going to tweak these numbers into numbers that are more likely for what you're going to be encountering in Mover, and I'm going to talk about how to apply this all to Mover in the next video. Just for now, there's one thing that I'd like to show you, and it's this picture. What you're seeing here are 3 different graphs for 3 different adoption rates or target horizons, however you want to call it, the different filter variables. So you can see if you change the filter variable, it's either a very quick adoption, a medium, or a slower adoption. And if I change, you can see it change in real time. Up here, it's 10, 5, and 3%. So if I change these values to, let's take a 20% adoption rate, you're going to see the yellow filter react really, really quick. If I dial that down to like, what, maybe an 8% adoption rate, it becomes a lot slower. And if I go down to even lower numbers like 4, for example, this is going to be slower than the 5% filter that you can see here. So the important thing that you should take away from this is, if you change the adoption rate of the filter, or in the inverse, the target horizon, as I call it, then your filter will change in the way it adopts that new value